Back in example 1a in part 1 of this video, we saw the sum of 1 over 2 to the n. We'll point out that we also wrote this 1/2 all raised to the nth power. This is an example of a geometric series. If you watch the introductory video to this lesson, we saw this sum evaluated in 2 ways. And in that video, we talked about how the second way was very intuitive, where we used a square that had an area of 1, and we added up all of the little smaller squares inside of it to get a total area of 1. I will point out that this sum was indexed with a start at n equal to 1. We found that that total was 1. Generally speaking, a geometric series is going to have the same kind of form where we have some ratio raised to the nth power. I will point out in this case, our ratio raised to the nth power was 1/2. But sometimes we may have a coefficient in front that I'll call a. In this case, a was 1. I have a blank here, but the word's already typed. R is the ratio of the series, and we don't look at geometric series when R is 0 because that would be boring. So what I want to talk about now is, when does a series like this converge and when does it diverge? So it will diverge if the absolute value of that ratio is bigger than 1. If we start off outside of a 1 by 1 square, the entire summation is not going to converge. It's going to diverge off to positive or negative infinity. But if the absolute value of R is less than 1, like we had up here, 1/2 is less than 1, its absolute value is smaller than 1, then the series will converge. And it converges to, I want to be specific here because it does depend on what we start the index of the series at. If I start the series indexed at 0, it will converge to a divided by 1 minus r. We will look at an example that addresses, well, what happens if we don't start the series at 0? We'll just have some extra terms that we need to account for. But what's important as we go through these examples looking at geometric series is that convergence or divergence completely depends on the absolute value of R. If the absolute value of R is less than 1, the series will converge, else it will diverge. So looking at example 2a, first we have to be able to identify what is a and what is r. I am going to do some rewriting of this series just to make it a little bit more obvious. The 3 in the numerator can be written as a coefficient to the fraction 1 over 2 to the n. And if you still can't see what r is, you can take that 1 over 2 to the n like we did before and put it in, just put 1/2 in parentheses and apply the exponent of n. So you still get 1 in the numerator and you do get 2 to the n in the denominator. So now I can see that a is equal to 3 and that r is equal to 1/2. Since the absolute value of r is 1/2 and that is less than 1, I can conclude that the series converges. So I know that when I add up all of these numbers, I will add up to a finite number. More specifically, for a geometric series, I know exactly what it adds up to. It converges to a over 1 minus r. I will point out that I'm just going to apply that formula because the formula can be used when n is 0, when the series starts at 0, and our series does start at 0. So we have a, which is 3, divided by 1 minus 1/2, which gives us our final answer that this series converges to 6. Example 2b starts off already set up to look like a geometric series. Just from looking at that, I can see that a is equal to 1 and r is equal to 3/2. When identifying r, it's important that r is everything that has the exponent of n applied to it. That's why I take the time to write it with this form so you can clearly see r is everything that has the exponent of n applied to it. In this case, r is 3/2 and its absolute value is a positive 3/2, which is greater than 1. And so this series diverges. It does not make sense to use the formula because this series does not add up to a finite number. Here in example C, I do notice that the series starts at 4. It does not start at 0, but I can also see that A is equal to 1 because there's a coefficient of 1 in front of that I don't see. Remember that R is everything raised to the nth power, and so R is 1/2. The absolute value of R is less than 1, and so the series does converge. Now let's talk about what the series converges to. The formula tells me that if the series had started at 0, it would converge to A over 1 minus R, which is 2. But our series starts at 4. Let's look at what the series looks like when it starts at 0. When the series starts at 0, it all adds up to 2. When n is 1, we have a half. Oh, rather, when n is 0, because it starts at 0, we have 1. When n is 2, a half. When n is 3, an eighth. And then when n is 4, I won't continue writing that. I'll just put when n is 4, I need to continue off to infinity. And I stopped there because that's what I'm looking for. Am I missing something? I sure am. I have when n is equal to 0. I have when n is equal to 1. For some reason, I skipped when n is equal to 2. So I need to move these over. When n is equal to 2, we get a fourth. And then when n is equal to 3, we get an eighth. And then I continue from n equal to 4. This is what I'm trying to solve for. And so I'm going to subtract 1, a half, a fourth, and an eighth from both sides of my equation. So I'm subtracting from the 2 on the left side to get a final answer of 1/8 that the series converges to. In example 3, we want to use a geometric sum. We'll talk about what that means, to write the repeating decimal of 0.08 as the ratio of two integers. So we want to write it as a fraction, basically, is what that means. So what is a geometric sum? A geometric sum, well, we've just seen what a geometric sum is. It looks like a sum of a r to the n. So our goal is to use this to write this decimal as a ratio of two integers. Now remember, we do know a formula to evaluate geometric sums. So the formula is how we will get the ratio of two integers. So let's start with that repeating decimal, 0.08 repeating. I'm just going to expand it out some by just repeating zeros and eights. And then let's think about what each of these digits mean. So we start off with a whole number of 0 that's added to 0 in the tenths place. That's added to an 8 in the hundredths place, 8 hundredths. That's added to a 0 in the thousandths. That's added to 8 10,000ths. And I'll just continue this process for a few more of the terms. I'll stop at 8 over 1 million. Plus ... The point here is that we do have a pattern of what these terms look like. In this series. This is a series. It's an infinite sum. So let's figure out what this pattern is. The ones that have the zeros we can completely disregard. So I'm really just interested in 8 over 100 plus 8 over 10,000 plus 8 over 1 million plus ... Each of the denominators in this expression are powers of 10. More specifically, the denominators are even powers of 10. Now going back to what we're trying to do, I want to be able to write this expression as a geometric sum. Remember, this is what we're trying to get this to look like, a geometric sum. I have added in, I know that in order to use the formula, I'll keep in mind that it would be nice if the index started at 0. So to get this to match this geometric sum formula, let's think about what is common to all of these terms. A is a common factor that we could factor out. Well, all of these terms have an 8 in the numerator in common, and they all have a 10 squared in the denominator in common. If I pull that out, I'm left with 1 in the first term. I already pulled out the 8, so I have 1s in all the numerators now. And in the denominator, we pulled out 2 of the factors of 10, so I need to subtract 2 from all of these exponents. Now, can we represent what's in the parentheses as an infinite sum that starts, this should be a 1, not a 8. And I want to make sure this 4 right here does look like an exponent on that 10. Okay, so now can we get to writing this as a sum? I can see that a is 8 over 10 squared. That's a constant in there. What is being raised to the nth power on the inside of parentheses here, starting with an index of 0? Everything on the inside of the parentheses has a 1 in the numerator, and in the denominator there is a 10, but the 10 is always even, and so it is a 10 squared. If we think about applying this, when n is 0, my exponent will be 0. Good. When n is 1, my exponent will be 2. When n is 2, my exponent will be 4. When n is 3, my exponent will be 6, so on and so forth. Remember, we combine those exponents by multiplying them. Now, this is a geometric sum that we should be able to evaluate. The formula says that this is equal to a over 1 minus r. In this case, a is 8 over 10 squared. And in the denominator, we have 1 minus r, and r is 1 over 10 squared, which it is worth noting is less than 1, so I do know that this series is convergent. And this equals 8 divided by 99. So it is the fraction 8 divided by 99 that gives the repeating decimal 0.08 repeating. Next, we have some properties of infinite sums. The first is a constant property that says if you have a constant that is not changing as n changes, you can pull that constant out in front of your summation. It doesn't really matter what I index the sum with here. These just need to match, and it will be the same. So it could be 0 and 0, 4 and 4, just depending on whatever you started with. The second rule I have up here is a sum rule that says you can break sums up into 2 separate sums. I just won't put an index on that. Well, I guess I can. If n was 1 there, then n would be 1 for both of these and would run up to infinity. This rule in particular is going to be helpful when you work on the practice problem at the end of this lesson. I think the second or the practice problem, yeah. So this first one here just looks like a geometric sum. You should think about what is a and what is r, and then apply the formula if you can, and pay attention to the index there. But this one here, this is a difference in the rule that we're talking about. Oh, we're talking about the sum rule, but conveniently, so not this one. This one will help you with that practice problem. It says you can break it up and think about the sum of just the first term, apply the formula to that one, and then think about the sum of just the second term. Apply the formula to that. Both geometric. Next, we have a theorem that tells us what the nth term of a series is doing if the series converges. So please fix that on your note sheet, cross out divergence, and replace that with convergence for me. The theorem says that if an infinite series converges, then the limit of that series as n approaches infinity is equal to 0, the limit of the nth term of that series. So again, remember, this a sub n is a sequence, and if I put it inside of a sigma, then it turns the whole thing into a series, but it is just a sequence that we can take the limit of. We've been doing that since 9.1. Now, this is not particularly helpful to help us figure out whether or not the series converges. This theorem starts with the assumption that the series converges. The converse of this statement is not true. So be careful that you do not use that theorem to say, oh, if I have a limit and I know that the sequence of that, I know that the limit of that sequence goes to 0. It helps me figure out that that sum is convergent. That's not true. That is not necessarily true. So for example, if I know that the sequence 1 over n goes to 0, the limit as n goes to infinity of that sequence goes to 0, does that mean that the sum of 1 over n converges? No, it actually diverges. We'll talk about that later. So this is just a counterexample to that. Now let's talk about how then can this theorem be used? The theorem says that if a series is convergent, it means that the limit of that sequence went to 0. There is another theorem, which is the nth term test for divergence, that will be helpful when determining if a series diverges or not. What this theorem says is that if you have a sequence and you take the limit of that sequence and you do not get 0, and you put that sequence inside of a sum, it will diverge. So this is a quick way to test for divergence. So let's look at an example of using this theorem here. So this theorem will be particularly helpful for quickly determining if a series diverges or not. So we have a series we're looking at. I want to point out it does not matter here that this series starts at 0 and that the theorem says 1 here. That's irrelevant. One term, a finite number of terms, is not going to change convergence or divergence for a series. So I can see here a sub n, what's on the sequence on the inside of that series is 2 to the n. Let's look at the limit as n approaches infinity of 2 to the n. As n gets really big, even if you want to change that into an exponential function 2 to the x, that grows off to infinity, which is not 0. So we took the limit of what was on the inside of the series and we did not get 0, so we can automatically conclude that the sum from n equals 0 to infinity of 2 to the n diverges. And I'm concluding that by the nth term test for divergence. So you'll notice a lot as we go through this chapter that I will be making a conclusion stating convergence or divergence, and then I'll be stating some test that I am using. Here's the first example you really see of me doing that. We're going to learn several tests, and then we'll go through problems where we use that test in order to determine whether a series converges or diverges. And it will be important that we state which test we are using. Example 4b, we have a series. Before I look at example 4b, I want to point out the theory behind this theorem, the idea behind this theorem, is that the sum of the terms you're adding things up, those things should not be getting bigger. If the things that you're adding up are getting larger and larger and larger and larger and going off to infinity, then your series is definitely not going to converge. More generally, if the things that you're adding up, if they are not going to 0, then your series is not going to converge. Then your series will be diverging. That's exactly what the theorem says. The terms of the things that you're adding up, their limit needs to go to 0. If it doesn't, you're not going to be convergent. So let's see what's happening in example B. Here in example B, a sub n, everything inside this box, I want to know what's happening to that sequence as n goes to infinity. To help me evaluate this limit, I'm going to simplify this expression by dividing everything in this rational expression by n factorial. So the n factorial that was in the numerator, I will divide by n factorial. The 2n factorial that was in the denominator will get divided by n factorial, and the 1 in the denominator will also get divided by n factorial. We can simplify a little bit because these n factorials here will cancel. Do pay attention to the fact that that 2 is not included in the factorial. So I am left with 1 over 2 plus 1 over n factorial. As n goes to infinity, this 1 over n factorial will be going to 0, and we will be left with 1/2. 1/2 does not equal 0. So this sequence goes to 1/2 as you start to look at those terms, which then means if you start adding up those terms, you will not be converging. You will be diverging because this limit is not equal to 0. By the nth term test for divergence, the series diverges. And yes, I am asking that you state which test you are using. Tell me which test you're using in order to make your conclusion. Let's look at example C. In this case, a sub n is 1 over n. Let's look at the limit as n approaches infinity of 1 over n. That limit is equal to 0. So what can we say? Well, the nth term test clearly starts with if that limit does not equal 0. In example for A, we saw a case where the limit was not equal to 0. In example for B, we saw a case where the limit was not equal to 0. And in both of those examples, we went and we applied the test. We can see in red where we did that. But here, the limit is equal to 0. That's different. Because the limit is equal to 0, I can't apply the nth term test for divergence. So at this point, I don't know what the series does. I don't know if the series converges. I don't know if the series diverges. I don't know anything else more than when we started. All I know is that I cannot use that test to make a conclusion because the hypothesis of that test is not satisfied. That limit is not equal to 0, so I don't know what it is. We will learn about this type of series later. In section 9.3, we will learn what this series does. I want to point out, this is not a geometric series, right? We do not have r to the nth power. We have 1 over n. So this is not geometric. I will tell you for now that this is called a harmonic series. We'll see what that does. In example 5, we have that a ball is dropped from a height of 6 feet and begins bouncing. So a ball starts at a height of 6 feet and begins to bounce. So it hits the ground the first time and it bounces. And when it bounces to 3/4 of the previous height. So it bounces back up, but it only goes 75% of the way back up. So it only bounces to whatever 3/4 of 6 is. And then it will bounce back down, hit the ground a second time, bounce back up, but only go 75% of the way. So it'll be, there's the previous height, and it only goes 3/4 of that. And this pattern continues as it bounces, so on and so forth. Dot, 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 dot. We're being asked to find the total vertical distance traveled by the ball. So the idea is that we can represent this as a series. Well, let's start with the first vertical distance traveled by the ball that I will call D1 as it drops from the 6 feet and goes down. Well, D1 is just equal to 6, traveled 6 feet originally. Then the ball went up, that's more vertical distance as it bounces up. The second piece of that I'll call D2, which was 6 multiplied by 3/4. Notice that the ball traveled that exact same distance as it traveled back down. So I'll go ahead and add that in here to conclude that that total red piece is 12 multiplied by 3/4. I'm trying to find a pattern between these numbers. Let's see if we can see what's happening here on this next piece that I'll call D3. Well, as we went up on that first green piece, we traveled 6 times 3/4 times 3/4, which is 6 times 3/4 squared. And we traveled the same distance as we went down, 6 times 3/4 squared, to get a total of 12 times 3/4 squared. And this will continue on and on and on. So I'll just add dot, dot, dot. So far we have that the total distance, that I'll call D, is 6 plus 12 times 3/4 plus 12 times 3/4 squared plus dot, dot, dot. The pattern continues. Next, I would have 12 times 3/4 cubed. Let's see if we can write this as a geometric sum. The 6 in the front, I'll just leave as a 6. Plus, inside here, we have a common factor of 12, and we're adding 3/4 to the first power, 3/4 to the second power, 3/4 to the third power, powers of 3/4. So this is 6 plus 12, a geometric sum with 3/4 as the ratio, and the index starts at 1. There's a few different ways you could compute that. If you want to take a second and think about the formula that says when the index starts at 0, you get A over 1 minus R. So if I know that when the sum starts at 0, I would get 4, then when the sum starts at 1, it would be 4, and I need to take away the 0 term, because our term did not have the first term that started at 0. So when n is 0, we would get 3/4 to the 0. 3/4 to the 0 is 1. So this is 6 plus 12 multiplied by 4 minus 1 to get a final answer of 42 feet for the total vertical distance traveled by the ball. Trick series.